Welcome you all. In this session, we are going to discuss the symmetrical short circuit analysis using Thevenin's theorem. Outcome: after successful completion of the session, the student would be able to uh, go for symmetrical short circuit analysis using Thevenin's theorem. Symmetrical short circuit analysis using Thevenin's theorem. Before moving to that, fault analysis is done for the following reasons. The main reason is to determine the magnitude of fault current and fault voltage in the system, to select the rating of used relays and circuit breakers, and for relay setting and coordination, to check the MVA rating of existing circuit breaker when a new generator are added into the system, to design the grounding system properly. So these are the major things. To enhance these things, we go for fault analysis in power system. So an alternate method of computing short circuit is through the application of Thevenin's theorem. So in this session, we are going to see in detail how the short circuit analysis is done with the help of Thevenin's theorem. The short circuit computation method is faster and easily adapted to systematic computation for a large networks. So the computation is summarized in the 4 steps. An observation can be made here. Since the pre-fault current flowing out the fault point F is always 0, the post current out of F is independent to the load for a given pre-fault voltage at F. Step 1. Obtain steady-state solution of loaded system, that is the load flow study. Already we done it in the previous unit. Step 2. Replace the reactance of synchronous machine by their subtransient and transient values. Short circuit all EMF circuits sources, and the result is the passive Thevenin's network. The passive networks of which we got in step 2 at fault point by negative of pre-fault voltage in series with the fault impedance. Compute the voltage and current at all points of interest. So step 4, post fault current and voltages are obtained by adding the results of step 1 and 3. So following assumptions can be safely made in short circuit computation, leading to considerable computational specifications. So the assumptions are: all pre-fault voltage magnitudes are 1 per unit. All pre-fault current are 0. All the pre-fault voltage magnitude is chosen as 1 per unit, whereas the current of pre-current fault is chosen as 0. The first assumption is quite close to actual condition, as under normal operation of voltage is nearly unity. The change in current caused by short circuit current computation are quite larger, in the order of 10 to 20 per unit, are purely reactive, whereas the pre-fault load current are almost purely real. Hence, the total post-fault current, which is resultant of two current, can be taken into magnitude equal to large component. This justifies the assumption 2. So the each synchronous machine is modeled as constant voltage source behind reactance. Pre-fault voltage of unloaded system is assumed to be 1 per unit. The shunt element in transformer model that accounts for magnetizing current and core loss are neglected. Pre-fault load current are neglected. That means we are assuming it as 0. All series resistance of generators are neglected. A symmetric three-phase power system is considered. So these assumptions are generally made to reduce the calculation. So in order to that, we go for these assumptions. So coming to Thevenin's theorem. So the steps involved in Thevenin's theorem are: So what we need to do is, first we need to draw a single line diagram for the given system. Next, select a common base, find out the per unit reactance of all generators, transformers, transmission line and load. From the single line diagram, draw the reactance diagram, which indicates all the reactance in per unit of, we call them as the reactance diagram, right? So now reduce the reactance diagram, keeping the identical fault point. Find the equivalent resistance. Yes, with the keep the fault point alone. Remaining things you need to equate. So you will be getting the equivalent reactance. So this is what we call it as the Thevenin's equivalent circuit. From the circuit, fault current is equal to ETH, that is the voltage divided by the total impedance. ZTH plus ZF. ZTH is the Thevenin's equivalent impedance. ZF is the fault impedance at that particular point, because we leave the fault point alone. Leaving the fault point, remaining things will be equivalent. So the equivalent impedance consider all other part of the impedance. Next, to determine the current contributed by two generators, if generator 1, then the fault current into Z2 divided by Z1 plus Z2. Here just what we have done is the current division rule alone. So similarly, Ig2 is equal to If into Z1 divided by Z1 plus Z2. Then determine the post fault voltage is given by Vi plus del V, where del V is equal to Zi2 plus Igi. Determine To determine the post fault voltage, line voltage is equal to Vi minus Vj divided by Zij in series. So short circuit capacity If is equal to ETH into 2 divided by XTH. So using this, we get the short circuit capacity. So this is how the short circuit analysis is done with the help of Thevenin's theorem. Thank you.